Hello. So good evening. Welcome to today's live session. Today we will be solving assignment 5, which is related almost related to your we have this Eulerian Lagrangian measurements, and also we have some questions related to Streaklines, Streamline, Pathlines. Before that, in previous class, you were asking about fluid under rigid body motion. So, if you have any specific question that you want to solve, you can ask me. Do you have anything specific to ask in fluid under rigid body motion?
No, so not specific, but I
Okay.
was just mentioning it is not there.
Okay. So, like if you have uh, fluid under a rigid body motion, then like uh, can you answer a few questions? So, what do you mean by a rigid body motion? So, fluid is not a rigid body, right? Like it can deform. It can deform pretty easily. So, but when we talk about fluid which is undergoing a rigid body motion, what do you mean? So, what we generally mean when we say a fluid is undergoing a rigid body motion is that the relative distance and relative angles between 2 points in a fluid uh, they do not change. Like for example, like if we have any 2 points, and it is undergoing some motion. These are 2 points in a fluid. They are undergoing some motion. So, like if this is having a velocity v in this direction, hmm, and this will, and maybe this velocity is changing with some instant at a time. Whatever is the path that this point is following, this point will have the same distance with respect to this point. So, like this AB distance will not change. And what if we have three particles? If we have three particles, then this angle additionally, along with the lengths AB and BC, along with this length, this angle will also not change. Hmm. So basically, you can imagine like if this is a triangle, so this triangle will like remain in its the shape will remain intact, and whatever the motion this fluid is undergoing, this only thing that can happen is that the whole triangle rotates. Hmm. The distance between any of these 3 points will not change while this motion is occurring. So when can this happen? Like this can happen if we have a uniform flow. You have like the whole fluid is moving with a uniform velocity of u. Then obviously this all these 3 points will also move with a velocity of u, and this will be a rigid body. And also like if you have a rotation, if you have rotation like from a certain point in some reference frame, a certain point is at velocity 0, but any point at a distance of r is moving at a velocity of omega r tangentially to this point at every instant. Then what is this? This is a circular motion. So, but this is a rigid body circular motion. Why this? Because of this r, this proportionality to the like radial distance from one particular point. So when such a motion is also taking place, then also this condition will remain valid and the points will stay intact. However, if you have some other like point vortex situation, and due to that point vortex, there is some like rotation taking place, then your velocity may vary something like omega by r and like plus something else omega by r, or and other things might be there as well. So if this is the case, this is outside, like outside the point vortex, or a cylindrical, like moving rigid body. Hmm. Then this case there is some viscous rotation, and there viscous stresses will be there, and this will not remain this rigid triangle. This will keep on deforming. So wherever these viscous stresses are involved, then there, if viscous stresses are involved, there means there is some shear, deformation due to shear, and whenever there is shear, these angles will change, right? These angles will change, and you will not no longer have a rigid body motion of the fluid. Hmm. So, like generally these vortices, like cyclones and all, they are sometimes have are modeled using like two concentric cylinders. Inside this cylinder, some rigid body motion is taking place, like uh, kind of like the eye of a cyclone or something, where we will have some omega into r. But away from this, there is like this won't be omega anymore, but some constant, maybe some c divided by r, the velocity outside this cylinder. So here it is moving in a rigid body motion, but outside viscous, uh, like viscous stresses are there, shear deformation is there, thus no rigid body deformation is taking place. Okay, so basic concept is this basically. So if I ask you, uh, if there is a flow through a pipe, the velocity profile is a parabolic shape, attains a parabolic shape when it is fully developed flow. Hmm. So has fully developed all these concepts covered in your lectures here? Can you confirm?
Sir, what was that again?
Yeah, have fully developed flow, the concepts of fully developed flow covered in your lectures.
No, sir.
Okay, I will just give you a brief introduction to that. Hmm. So suppose you have a like pipe. Okay, you have a pipe, and some water is entering through that pipe, and it is maybe driven by some higher pressure is there on one side. Here some higher pressure is there, and here some lower pressure is there at the end. So water will flow this way. Now when it is entering the pipe, when it is entering the pipe, then it will carry some velocity due to this pressure. And since these walls are there in the pipe, at the wall, what will happen? A no slip condition will take place, right? There will be no slip along the wall of these pipes. Hmm. So, but since there is a pressure driving this fluid, this will try to push. But the effects of this wall uh, will keep the velocity very low near to the wall. So this is called a boundary layer. So there will be formation of a boundary layer where the velocity will be something like this. The velocity will be zero at exactly at the wall, and this will keep on increasing. And inside some layer, this will keep on increasing, and outside this, it will attain kind of a uniform velocity. Okay, but since it's a pipe, and this is a very like this was a finite region, after some time, after some amount of flow, the velocity profile, these two boundary layers will meet, and the velocity profile will attain this parabolic shape. And after it attains this parabolic shape, this will no longer change. This parabolic shape will no longer change. So this region is called fully developed. This region is called fully developed. Why is this fully developed? Because the velocity profile is no longer changing after like in this region. So wherever you look, whichever cross section you take, you will attain the same parabolic profile. Whereas this region, before the fully developed region, this is called developing. Develop. Why is this developing? Because like in this region, you won't have this parabolic profile. It will develop towards this parabolic profile. So you may have a completely linear when uniform flow when you are just about to enter the pipe, and due to the wall effects, there will be some formation of some viscous layers or the boundary layers, which will like grow till it meets merges with each other and forms the fully developed parabolic profile. Okay, so is that concept clear to you?
Yes, sir.
Okay, so what I'm asking is, in this fully developed region, when we have this parabolic profile, will you consider this as a rigid body motion?
So the fully developed region might be considered as rigid body motion because the shape is not changing at that point. But after that and before that, it is not as rigid body.
Uh, in this fully developed region, the velocity profile is definitely not changing.
Yes, sir.
So you may be tempted to think in the uniform flow region, whatever is happening might be applicable here as well. Because here in uniform flow, what is happening? Suppose you have 3 points. I'm drawing here. So you have 3 points like this: A, B, and C. In uniform flow, after suppose delta t time, if you search where are these points now, this would move some u delta t distance, right? This
Yes,
will
yes.
also move u delta t distance. This will also move u delta t distance. So after some point, after time delta t, your new points will be here, here, and here. Okay, but these distances, they have not changed, right? Because all of them have moved the same amount of distance, u delta t. However, if you think carefully about this fully developed flow, here what is happening? If you have a point here, like same thing, A, B, and C, but your velocity profile right now is not uniform. Your velocity profile is some parabolic profile, a non-uniform profile, right? So here the velocity is something different. Here the velocity is different. Here the velocity. So after some time, this point A will move some less amount. Maybe this point B moves a little more. C moves a lot. So what you see is after some time, your points have moved, but the shape of this triangle has also changed, right? Because they have not moved in the same amount. They have not gone traveled the same distance, right? Because the velocity profile is not uniform. It is not changing, definitely. It's not changing with cross section, but the velocities of the individual points are still different, right?
Oh, yes, sir.
Hmm. So it will still undergo some deformation. So this is not a rigid point. Okay, this is not a rigid point. Okay, is this
Yes, sir.
clear?
Yes, sir.
So there is, are there viscous stresses here? There are viscous stresses, right?
Yes, sir.
Because there is some amount of shear deformation. The viscous stresses are there. Okay. For shear deformations, viscous stresses has to be present in a fluid. Okay. Let's. Do you have any other question related to this, or any from the previous assignments? You can discuss right now as well.
No, sir.
Okay. Then let's move to our this current topic. So the question is, the given question is whether balloon is launched into the atmosphere by meteorologists when the balloon reaches an altitude where it is neutrally buoyant. It transmits information about the weather conditions to the monitoring stations on the ground. Choose the correct statement regarding this measurement. This is an Eulerian measurement. This is Lagrangian measurement. Um, both A and B and none. Okay. So what we need to know here, we need to know. Where is the Eulerian measurement? What is Lagrangian measurement? So this we have discussed in briefly in our, I think, like first or the second uh, uh, session. So do you recall what is an Eulerian measurement? What is Lagrangian?
Yes, sir. In Lagrangian, we basically look onto a particle and we try to focus on that particle. But in Eulerian approach, we focus on a position, a particular position,
Hmm.
and then we try to focus on that.
Yes, that's exactly correct. So in our Eulerian approach, what we will do, we will focus on like a particular area. Hmm. And whatever this points will particles will come and go, we will just observe that. And in Lagrangian measurement, we will focus the point itself, and wherever it moves, we will and wherever this point moves, we will move with it and observe its motion. Or a group of points, for example. Group of points also we can like follow in a Lagrangian measurements. In Eulerian, we will not do that. If it if a point moves out of our region of interest, then we will no longer take any data from that point. So here, what is this? This is this a Eulerian or a Lagrangian measurement system? So when it is it measuring? It is measuring uh, when uh, when it is neutrally buoyant. It transmits information about the weather condition to the monitoring system. So it is measuring only after it is neutrally buoyant. So do you understand neutrally buoyant?
So not changing its position.
Not changing its position is not very accurate. So neutrally buoyant, buoyant you understand, right? What is a
Yes,
buoyant
yes,
word? What does it relate to? It relates to the force of buoyancy, right?
yes.
So
The
where does the
amount of
force of buoyancy come from?
weight the balloon will disperse on the
Yes. So this
this
weather
is
balloon has a different gas inside. So it may be hot gas or like generally it is hot gas or helium maybe. So some lighter weight gas so that it can rise up, right? Hmm. So it has some other fluid, and the atmosphere has a different fluid, right? So the density inside this balloon, let's say it is some rho b, and outside this is some rho a. Hmm. So two forces will be acting. One is the gravity force, right? So gravity force is rho v into volume of the balloon into gravitation force, right? The gravitational acceleration, small g. This will act downwards. This is the force due to gravity of the earth pulling it down. And along with that, there will be another force because since it is displacing a fluid, so there will be a buoyant force, a buoyancy force. So that is density of the air surrounding this hot air balloon into the volume of the balloon into acceleration due to gravity, but this will act upwards, right? Correct.
yes, sir.
So, what you can see, what is the net force due to this? The net force will be something like rho b minus rho a into v into g, right? So, what we can see, the net force due to this buoyancy and this gravitational force, it comes down to the difference in density. Correct. It comes
Yes,
down to
yes.
the difference in density. If the density difference in density is large, then there will be some net force. Either it will sink or it will rise up. Hmm. If your whatever you are putting in the water, like suppose you are putting something in the water, maybe a piece of metal. The metal's density is large than the water. So if then it will sink, right? Then the
Yes,
gravity
yes.
will win and it will sink. Now, if you are putting like a gas balloon in water, then what happens? The density inside the balloon, the air density, it is much less compared to water. So this will instantly like rise up. Even if you are like leaving it submerged in the water, this it will rise up. Correct. That then the buoyant force will win. The buoyant force is greater than the gravity force. Correct.
Yes, sir.
But there will come a point when these two are equal. If these two are equal, then these two forces will cancel each other out. So when this happens, this is called neutral equilibrium. Okay. When the densities of the surrounding fluid and the density of the object itself is same, then gravity and the buoyant forces will cancel each other out, and the object will be considered as neutrally buoyant. Okay. So now read the statement again. When the balloon reaches an altitude where it is neutrally buoyant. So what does this mean?
The density is equal.
Yes. So when a hot air balloon starts at the ground, then the hot air inside the balloon uh, has a lighter density, right? Because it is hot. So the density will be less, right? So we have studied from our ideal gas law equations. If temperature is higher, then your specific volume will also be higher, right? If your specific volume is higher, that means your density is lower. So if temperature rises, density will fall. So at the ground, the air inside the hot air balloon will have lower density compared to the surrounding air. But what happens when the balloon rises? When we rise in the upper levels of the atmosphere, the density also keeps on falling. So there will come a point when the air density inside the hot air balloon will be equal to the air density outside at that altitude when it has reached a certain amount of height. So that is what has happened. So the balloon has reached a certain height where the density of the surrounding air is equal to the density of the balloon. So it has now got the same density. Okay, is the concept clear?
Yes, sir.
Hmm. So now the question is very different. Question is whether this is an Eulerian, like if you are a neutrally buoyant particle, is this an Eulerian measurement or a Lagrangian measurement? Right? Balloon is neutrally buoyant, so it is a neutrally buoyant particle. For a neutrally buoyant particle, the particle which has same density as the fluid itself, is this an Eulerian measurement or a Lagrangian measurement? That's the question. So I will guide you in this particular question. The answer will be that it is a Lagrangian measurement. Why? Okay, here they have given some explanation as well. I will like try to follow this explanation. So yeah, so I don't know why they have given this note. Since weather balloon moves with air and is neutrally buoyant, following individual fluid particles as they move through the atmosphere. So so it is a Lagrangian measurement. Okay, the explanation is not that good. So I will like explain it to you. So if it is a neutrally buoyant particle, so if a particle has the same density as let's say whatever fluid you are measuring, then it is expected that whatever forces acts on the fluid at this particular point, it will act like behave the same way for the particle as well because it has the same mass, right? If there were fluid particles instead of this foreign particle, then the fluid would have moved in some way, right? If instead of this particle there were fluid here, then the fluid will have some motion.
Yes,
Now,
sir.
since the mass of this particle and the fluid are same, then this particle is also expected to have same motion. So since this rho of this particle is equal to the rho of the fluid, both are expected to undergo same motion. So if this particle is moving like a fluid particle itself, and we are taking measurements from it, that what does that mean? That means it is a Lagrangian way of measuring things. Why? You are following a particle. You are following a fluid particle. Okay. Is the concept clear? Do you have any questions related to this?
No, sir.
Hmm. So since this is moving along with the fluid itself, this is now Lagrangian measurement and not an Eulerian measurement. Okay. So the answer will be this is a Lagrangian measurement. Okay. Let's go to the next question. So next question is also very similar. So here you have two scenarios. One scenario is there is a tiny neutrally buoyant electronic pressure probe that is released into the inlet pipe of a water pump and transmits these many readings per second as it passes through the pump. So one is neutrally buoyant, and for the measurement 2, what we can see is that the measurement 2, the probe is fixed at one location. So this is fixed and this is neutrally buoyant. So it is asked whether one is Eulerian or Lagrangian and whether two is Eulerian or Lagrangian. So what will be one? Measurement one, is it Eulerian or is this Lagrangian?
Sir, both is a Lagrangian.
Okay.
And
So
two is surely Lagrangian, but one is maybe Eulerian. I don't know.
So if it is neutrally buoyant, what does that mean? It will move along with the fluid, right?
Yes,
If it moves along with the fluid, it behaves exactly like a fluid particle, right?
yes,
Hmm. So if it is behaving like a fluid particle, whatever measurements we are taking from it, it is as if we are taking measurements of a fluid particle itself. Correct.
yes, sir.
So if we are taking measurements of a fluid particle itself, then it is what? It is Lagrangian, right? Because we are
Yes,
following
yes.
a particle along its course. So what will be for neutrally buoyant? Will it be Eulerian or Lagrangian?
Lagrangian.
Lagrangian, because it is behaving like a fluid particle itself. Hmm. So whenever you have a neutrally buoyant sensor of any kind, like in the previous example we saw a hot air balloon, and here we are seeing like an electronic pressure probe that is basically released inside the fluid. Or whatever you are trying to measure, you may have something else as well. So whenever you have anything that is neutrally buoyant, it is a Lagrangian. It is like Lagrangian way of doing things because it is behaving like a fluid particle itself. So this is Lagrangian. What about the second question? The second measurement?
Yeah, that
Same.
is Eulerian.
This is Eulerian, right? Because this
Yes,
is fixed. This
fixed.
is if this is fixed. Now fluid particles are moving past it. They're coming and going, right? Hmm. So it can only take measurements whatever is nearby. So and in its nearby field, fluid particles are like coming inside and like leaving, but it is in spatially it is probing us the same area. This is exactly the concept of a Eulerian measure. This is this is an Eulerian way to do things. Like focusing on a particular volume or particular volume, and whatever is happening, like if fluid particles are staying inside or they are coming in and going out, whatever is happening, we are measuring. Hmm. So this is an Eulerian way of measuring. Okay, so two is Eulerian, one is Lagrangian. So this will be option two. One is Lagrangian, two is Eulerian. Is this clear? This Eulerian measurements and Lagrangian measurements, the concept is clear.
Yes, sir.
Yeah. So let's move on. So now it's a new topic. So consider steady incompressible two-dimensional flow through a converging duct shown below. Simple approximate velocity field for this flow is given, where u0 is horizontal speed at 0. Note that this equation ignores viscous effects along the walls, but it is a reasonable approximation throughout the majority of the flow field. So what is the question? The question is calculate material acceleration of fluid particles flowing through the duct. So do you know how to solve this? It is asking to calculate material acceleration for fluid particles. So here also some concept of your Eulerian and Lagrangian measurements is actually needed. So can you tell me one thing? Is this velocity field Lagrangian or Eulerian?
It is Larian, sir.
It's Eulerian, right? Because we have two coordinates. We have x and y, and here the x and y coordinates are defined. So, like whatever the fluid particles are coming inside and they are leaving, they are means the velocity at this particular point is given, but the fluid particle velocity will change when they are coming inside and they are leaving. So this is the Eulerian way to describe things. Now, when we are calculating fluid, like we are doing fluid mechanics, we need to calculate the forces acting on the fluid particles and the way they are moving and all. So, how to calculate the dynamics of anything? We have one equation which is F is equal to ma. This is the Newton's second law of motion, right? Now we have to somehow represent this fluid dynamics also in terms of this Newton's second law of motion. So is this equation, Newton's second law of motion, Eulerian way to describe something or Lagrangian way to describe something?
That is a Lagrangian way.
There is a Lagrangian way because we are following a particle, right? Whatever force is acting on a particle and however the particle is moving. But in when we are studying fluid mechanics, it is not very convenient to always work in the Lagrangian way. We prefer to stick to the Eulerian methodology. But since this equation is not valid for the Eulerian framework, we need to somehow calculate this acceleration. We need to calculate this Lagrangian acceleration uh, using this Eulerian velocity. So this will not simply be your dvt or del v del t. It will not simply be this del v del t. Why? Because this is Eulerian velocity and this is Lagrangian velocity. Both of them will be different. So when you are asking for this material acceleration, what is actually meant by this is your Lagrangian acceleration. Material acceleration is what we will put in the our uh, equation of motion. What we will put in our equation of motion when we are calculating our when we are calculating our velocity through the applied forces. So there is like um, there is a formula that can be derived, but like the derivation, I think you will find it in your recorded lectures that I will that is I think is this covered? Material acceleration should be covered, right? If it is given in this assignment, it should be covered.
Yes, it is. It is
Yeah.
covered. Yes.
So, what the concept is basically, I can explain the concept. So, you take a like small volume, and you take any fluid property. no, velocity is just one of them. Just take any fluid particle property. What is happening is basically the fluid particle is changing inside the system. Hmm. Let's say like velocity only. Let us say. So we have del v del t. It may change with time inside this particular system also. This is like the Eulerian acceleration, if you may say, Hmm. if you may define it like that. Hmm. And also there will be some like outflow and some inflow. So accounting for all that, we can define a material derivative, material time derivative, which is different from your del t, your usual derivative. So this material time derivative of anything, here we will do for velocity since we are trying to find acceleration. So this is defined as del t of v. This is basically whatever is happening inside this, and the flux change. So the flux change is v dot grad. So this will remain constant for all properties, and here we put the property that we want. Here this is v itself, so we'll put back v. So like if we were doing this for density, then what would have happened? Del rho del t. This would have been del rho del t plus v dot grad. So this v will still remain. So this velocity is not because like this will not be rho. This velocity is there because of the outflux and influx. Where the velocity will be required. Okay. So this is basically this ddt. This operator is called material derivative. This is called material derivative. So what we have to do is basically find this. This you can calculate. So yeah, can you do this? Del
Yes,
t will be 0, right? This first term is
yes.
0. This first term is 0 because there is no t term there. You have to calculate the second term. So your second term is basically you have your v. This I will write later on. Dot okay, v dot grad into v. V dot grad operated on v, because v dot grad will be an operator. So this is operated on v. Yeah. Can you calculate and tell me?
Sir, I think it is
Hmm?
C. C. B u naught plus bx ik plus by square jk.
Yeah. B u naught plus b right here. Uh, this minus and minus will be plus. Then this is is this C? I think it's B. Check your calculations once. So this I have expanded. Here I have expanded this. So v dot grad I have expanded. U0 plus bx in del del x, right? So x will be multiplied with x. So this is the x term for v, and this is the x term for this grad operator. And here
Yes,
also
yes.
same thing. This is the y term for v, and this is the y term for grad operator. Now, when I am doing del del x of v, what I am doing, I am keeping y constant and I am differentiating with respect to x. So, if you differentiate this velocity with respect to x, what will you get? You will get b, b I cap, right? B
Yeah,
I
yeah,
cap.
yes.
Hmm. So b I cap I have multiplied here in the first term, and here del del y of v you will get minus b j cap. So minus minus will be plus, and there is another b multiplied. So this is b square y j cap. So I think which option is coming?
It's A.
A is coming, right?
Yes, sir.
Yeah. So the answer should be yes. The correct answer is A. Okay. The mathematics part is pretty straightforward. Just like you have to keep a little bit patience while dealing with this. Okay. Let's move to the next question. Uh, so here a steady incompressible two-dimensional velocity field is given. Okay, and the streamline equation we have to find. So how do you do that? What is a streamline? Can you tell me what is a streamline? I think this question can be like best answered if you actually answer the question like can two streamlines meet? Can two streamlines coincide? Can they meet?
No, sir, because streamline represents the tangent to the velocity vector.
Yes, exactly. So each point of the streamline is the like tangent to the velocity vector. Now, if you have two streamlines coinciding, what will happen? In that coincident point, there will be two tangents.
Yes,
But
sir.
like means there will be two direction of the velocity. That can never be possible. You can only have like one velocity field dimension. So, but like can I have this in such a way like when they do not cross, but they can just touch each other? Like one streamline is coming like this, and another streamline is coming, but this is just touching tangentially. This is touching and then again leaving. Can this happen?
Yes, it can happen.
Uh, how? There is some problem with this. Can you identify? There is some problem with this. Physically, like this is difficult. Why?
Yes, sir, we will have two velocity component at the
No, you will
intersection.
not have two velocity components here. You will not have two velocity components. Here the tangential directions is only one, right? Both of these curves have like they are meeting at a point and they still have one tangent itself. Like for example, if you want an example of such curves, let's say y is equal to x square and y is equal to minus x square. Now, if you plot these two curves, then you will have this and this. Now they meet at x is equal to 0. And tangent for at x is equal to 0 is this y is equal to 0 straight line, x axis, right? For both of them. So here the velocity, the tangent is still in the one direction, but can they meet like this?
No, sir, they cannot.
Why? This will actually violate your conservation of mass. Why? What will happen to the fluid in between these two streamlines? So that is basically the question. So, like if you have two streamlines, they are you will have some velocity field along the streamline. So no fluid can ever cross a streamline, right? It cannot
Yes,
go
sir.
the other side of a streamline. But some fluid was inside between these two streamlines. Some fluid is here as well. So how is this happening? So the question will be this. This can only happen if the velocity field is zero. If the velocity becomes zero, then these problems will not arise because this is a null vector anyway.
Yes.
Okay. These are separate discussions. Now, well, here our velocity field is given, and like this is a very well behaved velocity field, unlike uh, this, where you will will not have any problem here. Uh, so it is asked to find the streamline equation of the streamline, and parameter c is coming here. You can see in the options. Parameter c is coming. What does this mean? Basically, this velocity field is valid for some like x and y for a whole range of or for a whole domain. So, like you will have multiple streamlines. All these streamlines can be obtained if you just change the value of c. Whichever initial point you get, you will get this value. Okay. So let's first find this. So how do you do? How do you do this? We have this formula, right? How do you obtain this? U and V is basically this. Your velocity field is ui cap plus vj cap. How do you obtain this? So any like at that particular point on the streamline. So if you take a particular point, your like um, x and y slope will be this, and here you can say the x and y slope will be this. So you are just equating this, nothing. Okay, this is clear.
Yes, sir.
Hmm. So you can put your u here, zero point 0.5 plus 0.8 x ui 1.5. So the variables are already separated, all the x's here, all the y's there. This is now just an integration problem. So can you integrate this? This is here some constant will be there. I can like since point 0.8 is on both these things, I can simply like take it something like point 0.8 ln 8. This arbitrary constant, this is also an arbitrary constant. You can take it as c, and like you can take it. So if you take antilog, this will become zero point 0.5 plus 0.8 x into 1.5 minus 0.8 y. This is equal to a, or as here it is given c. Just take y on one side, if you take c on other side, you should get some. So this is 1.8 something, right? So I think the option D fits. 1.5 by 0.8 is 1.875. Okay. Could you solve this?
Yes, sir.
Hmm. Okay. That's the correct answer. So here, like you, some form of function is given. So, like if you try to visualize this, so this is like in the form of y is c, and then some like a plus bx plus some d is given, right? So something like this. So what should it look like? So this is basically this, right? If I this is C. So this is basically some capital Y into capital X to C. So this is like a hyperbolic parabola, but origin shifted. Origin is shifted, and also there is some slope added to X. So this the like the axis will also be slightly tilted. So whatever wherever is the this origin shift and whatever is the slope is there, it will still look something like this. Okay. Did you understand what I did here?
Yes, sir.
Hmm. So it will look something like this. When, however, we vary our C, we will get different kind of curves. Hmm. So if C is positive, we may get like this and this, and if C is negative, we may get this. Okay. Let's move to the next question. So locus of fluid particles that have passed sequentially through a prescribed point in the flow is called a. Okay, yeah, this is a simple definition question. So can you answer this?
Yeah, pathline, sir.
Is it pathline? What is pathlines?
Locus, given identical fluid particles.
So pathline is basically path of a particle. Hmm. So if your particle is moving like this, when we are following this particle, this is pathline. Okay, right. Suppose you inject like a dye into water. This is the like basic example that is given always. So if you inject dye, uh, what the path that you will take, will it be same as like the thing that you can see? Will it be same as this? It won't be same as this, right?
Different.
Because the dye will move along the path, and you will no longer see the dye in the point where you originally the dye was present. It has already moved away. But what you will see is basically uh, maybe this is the injection point. This is the injection point. Whatever particle, fluid particle has come here, whichever and like, and they are now at a different location, and they are now at a different location. Maybe this particle was once here, hmm, and this particle was also once here, but now has gone to some other point, and this particle was also once here, and now has moved to this point. And if you connect all these particles, if you connect all these particles, then this is called a streak line.
This is true.
So streak line, the best example of a streak line is this dye injection. Hmm. So if you have a dye continuously injecting at a particular point, all the color, like if you are injecting a red dye, then everywhere that you see red is basically, if you join all those points, then this will give you a streak line. All those points are basically at some point of time they were exactly at the point you are injecting the dye. And path line, if you just followed one single particle. Wherever it is going, if you follow that particle, whatever the path that it is tracing is your path. Okay. So what is the answer of this particular question?
Streakline.
Strictly. Okay. You know pathline, streamline, and this is just a made up word. This is nothing. So all these three are covered. These are very important things. Pathline, streamline, streakline, like for analyzing fluid flows, these are very extensively used, and these concepts are very important. So it's streakline. Let's go to the next question. Find the unit vector normal to the streamline at point given, the point is given, and time is given if the velocity field is given by this. So what you have to do, you have to find a vector normal to the streamline, not the streamline itself, but a vector normal to the streamline. So how will you do that? So streamline, what we do? Streamline, what we do is your dx dy. This is basically u by v, right? And whatever if your slope is this, and this is u and v, you will u and v both are function of x, y, and t, right? If it is three dimensional, then it will be x, y, z, and t, correct? U and v. This is correct. Did you
Yes,
understand
yes,
what I said? Yeah. If it is a 2D flow, then only we can use this equation. Okay. So this is x, y, and t. So if your x, y, and t is prescribed, then your u by v is a constant.
yes, sir.
U by v is a constant. So what is this equation? This equation just states that your dx dy is a constant. Correct. Because here your x, y, and t are all specified. Correct.
Yes, sir.
So this is a constant. So this is your streamline slope at that particular point. Correct. Hmm. Now what you want is like a unit vector normal to the stream. So what you will do? You have done this in your school. So dx dy, if this is equal to m, what is if this is a straight lines equation? What is the equation normal to this? Dx dy, this is equal to minus 1. Correct.
Yes,
You
sir.
have definitely done this. I'm pretty sure you have done this in school. Like if this is your straight line equation, your normal to that particular straight line, your equation is this. So you will exactly do that. So the equation, like the normal, yeah, the normal straight lines equation is dx dy is equal to minus v by dt. Correct. You can do it in this way. You can also actually find the equation of a streamline, then again, like find the equation of a normal. That also you can do. Okay, whichever way you find easier. Okay, so can you solve this? So here the vector is asked, so any of these equations you can solve. So it won't make much of a difference in solving of this question.
answer is b 1 by root over of 5 I cap minus
Hmm.
2 by root over 5 j cap.
Yeah. So how did you get this?
At the x and y coordinate, we find the velocity and then we differentiate it with respect to y. Then we get the perpendicular with that velocity vector.
Okay. So let me just put this. Okay. Let me solve with the this Excel streamline Excel. So if I just put the values here, u is 2xy. 2xy means minus 4, right?
This is for
And this is y square t. Y square t is 2.
2.
This is minus 2. So actually, like you can do it from here only. Yeah, actually you can do it from here only. So dx dy if it is said minus 2, huh, so this is basically like your dx. I'm just rearranging nothing else. Dy, let this be minus 2. This is so for your this is for my streamline, right? This is for my streamline. So this is my streamline. So if I have like for this is dx, this is dy, it is given. So I can from here only I can actually find my like normal direction. So my normal direction will be one I cap plus two j cap. Yeah, this should be okay. Let me like explain it properly. Let me just solve this equation. That will be better. That will be even better. So if I this is the equation. So you have this right minus two y plus some constant, right? See, you can simply take this as this. Now you can always use the formula for the normal to this straight line. What is the normal to the straight line? This is basically the coefficient used as a vector 1 plus 2 j cap, right? These coefficients, these represent the normal I cap plus 2 j cap. You just need to uh, like you are asked to unit vector, right? So you need to normalize this, or like uh, you need to make this a unit vector. So the direction you need to make the magnitude of this vector as one. So what you will do, you will simply one plus one square plus two square. So the answer that you will get is root 5, sorry, root 5 I cap plus 2 j cap. Correct.
Yes, sir.
Hmm. So this should be your normal. Hmm. And obviously, like there are two normals because either direction you can go. Hmm. So your final answer should always include a plus minus. So let me check whether yeah they have got this itself. So the other way that I was uh, yeah. So the other way that I was trying to like show you which is easier I think if you have uh, like inverted it earlier itself. So the other way that I was trying to show is if I have this dx dy and so the unit normal as like earlier I said this will be minus dy, right? This is basically equation which is perpendicular to this. So if I have this, then this is my slope itself. Dx minus d is equal to dy by u. This is my direction itself. So my direction will be actually minus v I cap plus uj. This is the direction of normal. And this you can understand because your what is the direction of your velocity field? Your velocity field is u I cap plus vj cap. So what is the direction that is normal to this? It will be minus v I cap plus uj cap, right? Is this clear?
Yes, sir.
Hmm. You can like simply do a dot product and find out like this is minus u v and this is plus u, so they cancel out. So whatever, whenever your vector is some a I cap plus b j cap, what is your perpendicular vector? It is b I cap minus a j cap. So you can simply put the values now and make it a unit vector. If I simply put the values now, v's value I got as 2, so this is minus 2 I cap, and u's value I got as minus 4, so minus 4 j cap. And if I simply normalize this vector, and I will get the same answer, which is this one, C, right? Okay. If you have any like problem understanding, please let me know. Okay. If I'm like skipping steps or like I'm going fast or if I even if I'm going slow, then also you can tell. Okay.
Okay, sir.
Uh, all right. So the next question is, I have velocity components. Velocity components are given, and we have to determine streamlines subject to x is equal to x naught at t is equal to t naught. So my x and t naught are given. I think my y naught is also given. It's not mentioned here because I can see y naught in the options. Yeah, I think y naught is also given. So x naught and y naught and t naught. These three are given. What I have to find out? Equations of streamlines. On y naught is not given. Maybe I don't know. Okay, let's first do if we require y naught, we may put it. So x naught and t naught they are mentioned here. So we will simply use our standard technique. Have you done these questions? You have not done this question, right?
No, sir.
Yeah, you told me in the previous class that the assignments you get are different. Okay, so we just need to like integrate this. So this will be a function of time, definitely. But like in our integration, this won't make much of a difference. Can you integrate this and tell me? So x by 1 plus t. So this is 1 plus t. Dx by x. This is ln x. Right. I am directly integrating this. This 2 plus t. That's ln y plus some constant. Let's say ln c. So if I take antilog, this is x to the power 1 plus t. equal to y to the power 2 plus t by 2 into c. Now given is x x naught at t naught. I think y naught is also given. It's just not mentioned. So at t is equal to t naught, this point is at x naught y. If we just put it here, then x naught 1 plus t naught, this becomes c, y naught 2 plus t naught by 2. So why we put this condition? To find out c. So we can simply find out c from here. And what we will get here is basically x by x naught to the power t naught. This is equal to y by y naught to the power 2 plus t. Sorry. Okay, I made a mistake, I guess. No, t naught is also there. No? So this won't be as simple. So this is x 1 plus x to the power 1 plus t divided by x naught to the power 1 plus t. I cannot take this in bracket because t naught is also there. And here similarly 2 plus t by 2 by y naught 2 plus t not by. Do you have any matching options for this? Hello? Did you arrive at this? Hello? Yeah, can you explain how you got the answer? Hello?
Yes, sir.
Hmm. So, have you got the answer?
Sir, it will be d y by y naught is equals to.
Yeah, how did you get the answer?
So we
Like, did
take
you?
the common.
Hmm.
If we take the 1 plus t common,
but inside this is T naught, right? So what I can see is they have like kept y on the LHS, so I will do the same. So let me use a different color pen and shifting here on the top side. So they have kept it y. So what I have to do is basically uh, take everything on the other side and like uh, exponent this 2 by 2 by 2 plus t, right? So if I take that exponent, so for y naught this will be 2 plus t naught by 2 plus t. This is equal to. Have we proceeded in the same way,
No,
or
sir.
like I am doing some? Am I doing some mistake? Can you point it out? Okay, let me check the like they have done the solution here.
So they are they done it differently.
Yeah, they have done like one thing they have done good is that they have taken everything this side. I think like from here also I should be able to like arrive at this solution. It seems very difficult. So what they have done is they have like this is a smart move to do. Like they have taken all the t terms on one side and kept it there only. So they got a very nice expression for y. After they have got this nice expression, uh, yeah, they have got also got a nice expression for k for that same reason. Yes, you can do it this way. This is much better. Uh, like probably you can arrive to the same expression through this also, but this will be tedious. You can follow this. Simply take all the t terms on one side and then you take it. Just make it. Okay. Can we go to the next question?
Yes, sir.
So the velocity components in an unsteady plane flow are given. Uh, is this the same velocity field? This is the same velocity field, right? Yes, the same. So determine equations for path line subject to the same. Okay, so same conditions are given. Now we have to do path lines. So how do you do path lines? How what do you do for equations of path line? So when you like here,
So we will
yeah.
the same thing dx by u is equals to dy by b, and then we will get the what equation we will get. We will integrate that.
But
And
that will give you the streamline, right? That won't give you the path line. Because what is ds by u dy by v doing? ds by u by dy by v. This is
Yes,
making
yes,
sure your that the like direction of the slope dy dx is the same as the direction of your velocity field, right? It is making sure that, but it is not giving you the path line. So what will give you the path line? So when you think of a path line, what is path line? Can you like give the definition of path line? Is it?
so path line is like a, for all identical particles, it is a locus of all identical particles.
Path line is a path line can be said like if you are following a particular particle, then the locus of that particular particle is your path line. So wherever your particle is moving, and you take a particle, wherever your particle is moving, the path that it followed is your path line. Okay. Does this make sense?
Yes,
So
yes,
if you take a particular like particle and just trace where it has gone, then you will get the path line. Okay. So how do you find out that? So this is like a like Lagrangian thing, right? You are following a particle. It's like a Lagrangian thing, right? Hmm.
yes, sir.
Yeah. So and you have got your like position and you have got your velocity.
Yes, sir.
You will just like integrate your position with time. Okay, that's what. So if from x, this is giving the position of this particle at every point. Then this x is basically your uh, sorry, misquote this. X, if x is your position of a particle, then your dx dt, this will give you velocity, right? This should give you your velocity,
Yes, sir.
correct? So for your x component of your like position, x coordinate, uh, this this should give you vdt, your udt, correct? Hmm?
Yes, sir.
Your dx integration should give you vdt. If you are at like whatever your origin point is, let's say I'm doing with respect to time, so from t0 to t, correct? So this point at t is equal to t0 was at x0. I will put my this way. So x, so like this actually will continue to change. Okay. So let's see how they have done this. They have done it the same way. But yeah, so I had to like take the integration x. I needed to take it. I will put like ahead. had actually put the integration sign before separating the variables. Sorry. Yeah. So you have this equation, right? You will put the expression for it. So that's what I was thinking about. So we will put the expression of u here. So this is the expression of u. We put it here. Plus two. Now you separate the variables. Now you can integrate. This is not a problem. This by x, dt by 1 plus 1. So this portion is important. Like why I am taking this equation and not your dx by u is equal to dy by v. That will actually give me a very different answer. You can check and see that if you try to solve like dx by u is equal to dy by v, you will get a different answer because it is a different thing. It's a streamline, and this will give you a path line because at every point, like at every position x, you are solving for the velocity. We will now integrate this and we'll find out some expression. We will this is uh, both side will be log, so I can simply not write log here. This will be x by x naught into some constant. So this will be 1 plus t by 1 plus t. And here also you will have, if you do for the y component, you will have this. You can substitute v with 2y 2 plus t. So you will get dy by y here, and you will get 2 dt plus 2 plus 2 plus t. Again, if you integrate this, you will get y by y naught. And what will you get here? You will get 2 plus, yeah, some constant. Let's say if this is c1, this is c2, you will get whole square, right? Because of this 2. So this will come out, and this will be ln t 2 plus t, and this will be whole square. So 2 plus t by 2 plus t naught. Okay. Now you have two set of equations actually, and two constants. You will need to merge these equations because path line will be obviously of one curve only. So what is the condition that is actually given? Condition is given that this particle at t is equal to t0 was at x is equal to x. So t is equal to t0 is given here, was at x is equal to x0. So what you will do is basically substitute like y0, substitute out y0 from this equation, and then put this in this. So here you have 2 plus t by 2 plus t naught, and you have this y0 here. This y0 condition has not been given. So you can substitute out and put this in this. And actually, one thing that in this, since this is a path line, will it change with time? Will it change with time? It won't change with time, right? Because with time, the path line is remaining same, the particle is moving. So whenever you are like providing some time t, you will find the particle at a particular position. But this line equation will not change with time. So what you will do is put your time equation t and substitute in one of them. So let's do that. X by x naught 1 plus t naught here divided by c1, and this is t minus 1. This is equal to your time t. If you put this back in this equation, then you will get an expression for your you will get expression for like you will get your solution. Okay. Have you solved this?
So it may be d y by y naught is equals to 1 by 2 at 2 by 1.
This is coming. Okay.
Roughly, yes, sir.
You, but here minus sign is there. I don't think this will be an answer. This should be 2 plus t square. Right.
That's
From seeing these options, I can see that this is correct because there is 2 plus t square here, right? 2
yes,
plus
sir.
t.
It's
Oh, actually, I have
yeah.
done another mistake. Sorry, I'm like making a lot of mistakes today. So here, this will not be there. The integration constants will not be there, obviously, because I have already put the initial condition. Sorry, yeah, x naught I have put, right? T plus t naught I have put. So these initial conditions will also. Yeah, so this A will be the answer because I can see like from the form also only you can make this because 2 plus t square t naught square must be there, right? So
Yes, sir.
only one option is there. And above like here what should be there? One this is 2 plus t some whole square. Hmm. So yeah. So if you put this here, you can see like t if you substitute there is one minus one here, one minus one here. So this two plus t will be like this one plus and this term is there. So if you put this term here, you can easily say that this a option is the answer. Okay, did you get this?
Yes, sir.
Hmm. Okay. Do you have any other question for me? I
No, sir.
think this is the last. Yeah, this is the last question for today. So they have also done the same way. Uh, yeah, take. So let me repeat the steps because these are important. For streamline, what you will do? For streamline, you will integrate ds by u is equal to dy by v. Right.
Yes, sir.
Hmm. For path line, what you will do? Path
Pathlines
line,
we will
you have two equations because
yes,
like it is vector, so you will have two equations. This
dx by dt and
and this. Then you will get two equations. What you have to do? What is the next step? Next step is eliminate t. So t you have to remove. Hmm. Just like this, we have done here. What you have done, we have got two equations, right? This one and this one. Hmm. We have found out the value of t from this equation and put it here, substituted it here, right? The reason is because your path line will not change with time. The line will be same, only the position of the particle is changing. So your path line is actually constant with time. Correct?
yes, sir.
Yeah. Yeah. Okay. What happens? Like what? The only thing that we is left to be discussed is streak line. So what will you do when it is a streak line? Here also this actually like there is no this kind of geometrical conditions like there for streamline. Here also you have to solve these two equations. dx dt is equal to u and dy dt is equal to v. Okay. Here after solving this equation, what you have to do is basically eliminate t naught. So here you have t naught, right? What is T
Yes, sir.
naught? T naught is the time at which this particular particle was at the point x0 y0. Correct.
Yes, sir.
T naught is the time when the particle was at x0 y0 for path line. Now for streak line, what is happening is that the point was all means the definition of streak line is such that the point has always gone through x0 y0. Correct. Hmm. So the streak line will change with time, but this particular every point has gone through t0, so t0 is no more required. Did you understand the concept?
Yes, sir.
Hmm. So here what you have to do, you have to eliminate T0. Hmm. So this streak line will also change with time. It will be a function of time. You will no longer have T0 in this in your equation. Okay. So like this, you can find out this equation of this. All right. So if you have no other questions, then I will like end the session.
Sir, for a steady
Hmm.
flow,
Yes.
the streakline, streamline, path lines are all equal. So if that is a velocities component as given is such at a steady flow, so we have to
Hmm.
calculate streamline, path line for every other one, or just the same for.
So you like let's see. So if it is a steady flow, we will no longer have the parameter t.
Yes, sir.
So we will whatever path line we calculate is the same as streak line, right? If it is a steady flow, whatever path line we calculate, streak line is the same.
Okay, sir.
Hmm. And what will you do for the streamline? That also you can see that it is same because like for every dx by u and dy by v, those two will also be equal. Like if you like for a differential
Yes, sir.
equation.
Yes, sir.
So yes. So your question is, do you need to calculate it separately?
Yes, sir.
Is
Or
that your
we can
question?
just, or we
No,
can just calculate the.
you need not to calculate separately because
Okay,
those
sir.
will be same.
Okay, sir.
Hmm. Okay.
Thank you, sir.
Hmm. All right.